every second.
Yeah, give them a couple of more minutes. I see the Americans are waking up now, like Midwest, like Faidu.
Yeah, right. Okay, so we are now live on YouTube. All right, so I'm happy to welcome Teck Gan from Singapore. He will tell us on transfer of characters under the Howe duality correspondence.
Okay, thanks very much for the introduction. And so let me first thank Dima and the organizers for their kind invitation to give my first ever Zoom talk. Okay, I hope it is okay. So I don't have an iPad with a pen or anything, so I'm not going to try to annotate on the file. I'll just use this cursor to move around.
I'm sorry, just one technical comment. Slides are available in the calendar. So on the seminar website, there is a calendar, and in the calendar, there's a Dropbox link. And I will now share this Dropbox link in the chat also. Yeah, okay, please continue. Good. Excuse me.
Okay, so the big surprise is that I'm going to talk about the Theta correspondence, okay? And even though it has a slightly disguised as a Howe duality correspondence. Okay, so let me maybe start with just recalling what that is. So first, the notion of a dual pair. So I'll work over a local field F. Although for this talk, it will be, I will just implicitly assume that it is non-Archimedean, even though I guess it should be okay with Archimedean as well. So the setup was we have two pieces of data, a symplectic vector space, W of dimension, say 2n, okay, with the isometry group SPW. And then I'm going to consider odd dimensional quadratic spaces, okay? And for simplicity, I assume the discriminant is 1. Now, over a non-Archimedean field, there are two such quadratic spaces of a given odd dimension, okay? And so one of the spaces is split and the other one is non-split. So I will denote those two by V plus and V minus respectively. If you are working over Archimedean field, of course, there will be several more such quadratic spaces because they are classified by signatures, okay? So when you, in any case, when you have a symplectic vector space and a symmetric one, okay, a quadratic space, their tensor product will be naturally a symplectic space. And there's a natural map from SPW cross OV to SP of the tensor product, okay? And I guess the image of these two groups are mutual centralizers of each other in this larger group. And this is an example of a dual pair. Okay? So of course, you know, there's a full classification of this, and one could take Hermitian and skew Hermitian spaces over quadratic extension of F and so on. Okay, but in this talk, just for simplicity, I just to fix ideas, we just work with a symplectic and an odd dimensional quadratic space. Okay. All right. Now, for the symplectic group, there is the so-called unique twofold nonlinear cover, which is called the metaplectic group. Okay, and so I'm going to work on that level. Okay. Now it turns out that the metaplectic cover of V tensor W is actually split over the orthogonal group, and the splitting is not unique, but let's say we fix one somehow. Okay. So anyhow, we get a lifting of the previous map to this to the level of metaplectic group. Okay. Then after fixing a non-trivial character of the base field F, there is a so-called WIS representation of these large metaplectic groups, and we can pull it back by this arrow to get a representation of MPW cross OV. Okay, so these are maybe denoted by omega of sub V comma W comma psi. Okay. So I should say, if you have any questions, just feel free to interrupt and ask. Yeah, I noticed last week that when Dima gave his talk, he only has 16 slides, and I have almost double the number of his slides. So I hope that's not a problem. But okay. So if you feel I'm going too fast, so just please let me know. Okay. So for some reason. Okay. Now, under this setup, okay, so I guess the point of data correspondence is to understand this representation omega of MPW cross OV. You know, before you restrict to this product, this very representation is almost irreducible. It's a sum of two irreducible summands. But of course, once you restrict to this smaller group, it will break up, you know, into many pieces, so to speak. And we like to understand that decomposition. So that's what how duality correspondence or data correspondence is. More precisely, for if you give me an irreducible representation pi of OV, we can consider its so-called big data leaf to the other group, MPW. And one way of defining it is by taking the tensor product of omega with the contragradient of pi, and then taking the co-invariance under the diagonal action of OV. Okay, so this is one way of defining this big data of pi, which is a smooth representation of MPW. Likewise, you could take a irreducible representation of MPW. Okay, and as you say, as a matter of convention, whenever I work with things on MP, I will assume that they are genuine. In other words, they do not factor to SP. Okay, so this is, so pi tilde will be an irreducible genuine representation of MPW. And then likewise, by using the analogous formula, we can define a smooth representation theta of pi tilde of MPW. No, sorry, I guess this should be of OV. Typo here. Okay. So I guess the first basic result is so-called Howe duality principle is that this big data leaf, data of pi, is actually a finite length representation. Of course, it could be zero, but if it is non-zero, it is finite length, and it has a unique irreducible quotient, which I denote by little small theta of pi. Okay. Moreover, if you take two different representations, pi 1 and pi 2, then their small theta leaf are distinct if they are non-zero. Okay. We have the analogous theorem if we reverse the row of MP and O. If we start with a pi tilde, we have an analogous theorem. Okay, so now for the rest of this talk, I'm actually going to specialize to the case of equal rank. Okay, that is when m equals to n. In other words, dimension of W is 2n, dimension of V plus or V minus will be 2n plus 1. Okay, this is just for simplicity, because this case is somehow is a case where, because the rank are equal, so the roles of that these two groups play are completely symmetrical. Okay, if you consider it in general, of course, one group will be bigger than the other. So there's a bigger one and a smaller one. There's some asymmetry in this. And so I guess, you know, for this talk, I just prefer to focus on the case where, you know, picture is the same, whether you say it in one side or the other, because otherwise you have to say some special things for either the bigger or the smaller group in the process. Okay. Okay, so, and for an example of a good thing of focusing on this equal rank case is that one has the following theorem that I showed with Gordon Sabin some years ago, which is that if you consider the data correspondence in this equal rank setting, and of course it is between MPW and OV, but we can restrict from OV to SOV, okay? Because V is odd dimensional. The orthogonal group is simply the direct product of SOV with the center of OV, which is just a plus minus identity. Okay, so there's not much loss in the sense that, you know, if you have an irreducible representation of OV, it remains irreducible when restricted to SOV. In this equal rank case, when you couple the data correspondence with this restriction, you actually get a bijection. Okay, from irreducible genuine representations of MPW to the disjoint union of the irreducible representations of these two special orthogonal group. Of course, there's an analogous theorem in the Archimedean case where on the right-hand side, you will have many, many more terms, okay, parameterized by the signatures of the quadratic space. Okay, and this bijection is very well behaved. I mean, for example, it restricts to give bijections on the set of discrete series and also on the set of tempered irreducible representation. So for example, I could insert the subscript tempered, okay, on all these terms, okay, and you have a bijection. Okay. So this concludes my quick introduction to the Howe duality correspondence. And so I come to the other thing, the other terms in the title of the talk, namely characters. So if pi is an irreducible representation of, say, p-adic group GF, then one may consider its so-called Harish-Chandra character, okay? Which unfortunately is also denoted by Theta for some reason. And what is that? Well, it is a conjugacy invariant distribution on GF, okay? But it essentially is given by a function on the regular semi-simple locus, okay? So in other words, theta of pi, the Harish-Chandra character, so it's a continuous linear form on the smooth compactly sorted functions on GF, okay, to C, okay? And the fact that it is conjugacy invariant means the following. So of course, this space, the CC infinity of GF, is a GF cross GF module with action by left and right translation. You can restrict that action to the diagonal copy of GF, then that action becomes conjugation. Okay, to say that this distribution is conjugacy invariant means that it factors through this co-invariant space. Okay, so here I'm taking the diagonal copy of GF, which acts on GF by conjugation, and I would like to it factors through this co-invariance. Okay, and more concretely, if, for example, if pi is a unitary representation, you can define this distribution theta pi by taking an orthonormal basis of pi, and then taking the sum of the diagonal entries, diagonal matrix entries in the matrix of pi f. Okay, I guess maybe I should have written down the definition of pi f, but I didn't. So, okay, all right. So the fact that this sum sum is actually finite because our function is locally constant. Okay, I mean it's a smooth function. Okay, so as a result, this sum is actually finite. So pi f is a finite rank operator. Now, suppose pi is tempered, then in fact theta pi can be extended to a slightly larger space of test functions, namely the Harish-Chandra sort space, which I will denote by this math cow C. Okay, this space of function is contained in L2. Okay, and in fact, it is the space of functions that underlies Harish-Chandra's Plancherel theorem. Okay. So indeed, if you take f to be in this Harish-Chandra sort space, then the operator pi f is also defined, is also finite rank, can take the trace. Okay, so that's characters. Okay, so here's the question I want to discuss today. So suppose you take a pi and pi tilde, and they are data leaves of each other. Okay, so pi tilde is data of pi. And the question I want to talk about today is how are the characters of pi and pi tilde related? Okay, so I should mention that actually this question has been studied for a long time, okay, by Thomas Brechbinder. Okay. So I guess he has many papers on this related to this question. Essentially over the case when f is Archimedean, and typically under the hypothesis that one of the spaces, V or W, is much smaller than the other. Okay, so this is like at the other extreme from the hypotheses I put today, right? Because today I'm working on the equal rank case. Okay, in his papers, he most of the time assumed that one is working in the so-called stable range, where one space is much, at least double the size of the other. So he has a series of papers beginning in fact in maybe 1990, in the early 90s, and in fact the most recent one was a paper in a Journal of Functional Analysis, maybe just last year or 2 years ago. Okay, studying this question. Okay, so I guess as I mentioned, these characters are given by some smooth functions on the regular semi-simple locus, right? So one, I guess what Brechbinder was trying to do was to try to express, for example, the this function for pi tilde in terms of the function of the character of pi as an integral transform. Okay, so in particular, there was this relation is expressed by a certain formula which he calls the Cauchy-Harish-Chandra integral. And one of the reasons why he restricts to this stable range case was because you have to struggle with the analytic difficulties in working with this integral. You have to make sense of it. Okay, so what I want to do today was actually to try to think about this question from a more conceptual approach. In other words, one that is not so much based on formulas. Okay. Okay, so that's what I would do. So what do I mean by a more conceptual approach? So here's what we are going to do. So we want to compare two distributions, right? Theta of pi and theta of pi tilde. These are distributions on different spaces, different groups. And so in other words, they are linear functionals on different spaces of test functions. So how could you compare them? Well, you need to compare the space of test functions. Okay, so what we are going to do first, we are going to introduce certain spaces of test functions on the two relevant groups. We are going to define a notion of transfer of test functions from one group to another. Okay, now we are going to show that, so this transfer is not a function, it is a correspondence. Okay, it's kind of a relation between functions on MPW and functions on SOV. So it is like a one-to-many function, something like that. Okay. However, we are going to show that this correspondence actually descends to a well-defined map on the level of orbital integrals. As a result, you can pull back, for example, invariant distributions of one group to the other. Okay, and then so now it makes sense to, for example, pull back the invariant distribution theta pi from SOV to MPW. Okay, then now you're going to have two invariant distributions of MPW, theta pi tilde, and the pullback of theta pi, and it makes sense to ask whether they are equal or not. Okay, and we are going to show that they are equal. Okay, now you'll see that the definition of this space of test function and transfers are very simple and very conceptual. And when something is too neat, you may wonder whether there's any contents to it. But maybe it's just tautology somehow. Okay, I mean the definition is somehow makes it the statement a tautology, even though it may look like a pretty good statement. Okay, so well, at least I wondered that myself. Okay, so so the last thing I want to talk about is actually to describe this transfer in a geometric terms, which morally speaking means giving formulas. Okay, for it. Okay. Okay, so that's what this is the plan, okay, for the rest of the talk. Okay. Maybe it's the time to stop and ask if anyone have any quick questions before I go on.
Do you expect the transfer will be the same also when the rank are not equal?
Yes, I mean, the definition works in general. I mean, as I say in this talk, I just focus on the equal rank because, if they're not equal rank, I may have, whatever I say for one group, I cannot necessarily say the same holds if you work on the other side. Okay, but in this equal rank case, I really can say that. And in fact, I would just focus on, say, for example, MPW. Okay.
Mm-hmm. Okay.
Maybe I make a remark on in general, sort of, at the end. Okay, I did thought about making some slides for it, but then I am aware that I'm already, as I said, double the number of slides that Dima had last week. So I thought it should be okay to use all the time.
Maybe a little bit. So I don't have assumption on the stable range to construct the integral kernel, but in the stable range, I know that this is correspondence of characters.
Yes, okay, I see. Thanks for the clarification. I guess that's a okay. Thomas, right? If I suppose, yeah, because
it's nice to see
everyone's. Yeah, so I guess his remark was that he can write down this integral transform in general, but only the stable range can he show that the resulting distribution on the other group is the character of the data leaf.
Yeah.
I hope I say that correctly.
It's fine.
Yeah. Thanks. Okay. So so as I said, spaces of test function. Okay, that all will be very very simple and conceptual. So here it basically comes from this diagram. Okay, so what am I doing? I have my dual pair, right, associated to W and V. Okay, so now I put V epsilon because epsilon is a sign, plus or minus, right? Remember I said that there are V plus and V minus. So I don't want to keep track of that at the moment. Okay, so anyhow, I fixed my symplectic and quadratic space. I have my Weyl representation. I tensor it with itself essentially, or with its complex conjugate. I'm going to call this tensor product capital omega. Okay, and then I'm going to define two maps P and Qs to smooth functions of MPW and a smooth function of SOV. And the maps are very easy. They're just formatic matrix coefficients. Okay, so for example, if you give me a pure tensor in this tensor product, phi1 tensor phi2, I just take it to a function of on MPW. So its value on G is just essentially this matrix coefficients. Likewise for the other side. Okay, I'm going to define my space of test functions to be the image of these maps. Okay, this is a very simple definition. Not that you know what these spaces are at the moment, but at least they are defined. Okay. Okay. Now we can define the notion of transfer. So if you give me a function on SO, a function on MP, I say they are transfer of each other if there is a phi in capital omega that maps to F on one side and F tilde on the other side. Okay, now in fact it is better to put the plus and minus spaces together. Okay, so for example, I can define the space which I'll just denote by S of SOV plus minus. Okay, I just define as the direct sum of the two spaces that I defined when I had a fixed epsilon above. For MP, okay, we have defined, depending on whether we use V plus or V minus, right? We have two spaces of test function S plus. Okay, maybe I go back to the previous slide, right? Because here I fix an epsilon, so I should keep track of it on all my notations. So on MPW, I have a space called S epsilon. Okay. On the orthogonal side, I just have a space on the group SOV epsilon. Okay. So on the MP side, I have S plus and S minus. They are both subspace of the space of smooth functions on MPW, and I basically want to take their sum. Okay. Of course, at the moment, it's not clear that this sum is direct. Okay, but it will be. I'll mention it later. Okay. But or you can just say that I just take the outer direct sum of these two spaces of functions. It's fine. Okay. So anyhow, I define this, and then so I just look at these pairs, and I say that they are in correspondence if the plus components correspond and the minus components correspond. Okay. So this is just to sort of because as you see in the local Shimura correspondence, representations of MPW is like a disjoint union of the representations of SOV plus and SOV minus. So I think it's better to group the SOV plus and SOV minus together. Okay. Okay. So one sort of obvious observation to make is that transfers always exist. Okay. Why? Because the spaces, these spaces of test functions are defined to be the image of P's and Q's respectively, right? So if you give me any function, any F, I can find a phi so that P phi is F. Then I just take Q phi to be the transfer. Okay, so transfer always exists. So this is in contrast to, for example, endoscopic transfer, where you had a hard time trying to prove that transfer exists. Okay. Okay. So so I have defined the spaces of test functions, and I have defined the notion of transfers. Okay, but the definition is very simple, but it doesn't mean you know much about those spaces. So it's good to formulate some properties of these spaces to see what they are. Okay, so so the first, this lemma says that if you look at the space of test function on, for example, on MPW, okay, recall that this is the sum of S plus and S minus. Okay, now in fact this sum is direct. Okay, as I say, it's a direct sum. The space, the functions themselves are contained in a Harish-Chandra sort space. Okay, and they are sufficiently big to contain all compactly supported and smooth functions. Okay, so it is somehow valid to call these functions test functions. Okay, because you at least want them to contain the compactly supported functions. but they are not so big, so much bigger because they are still contained in the Harish-Chandracharacters space. Okay, so likewise on the other side, on the orthogonal side. So if I had not worked in the equal rank case, right, if I had worked one group is bigger than the other, I would not be able to have this statement that both the spaces are contained in the Harish-Chandracharacters space. Okay, it would be the case for the smaller group, but it will not be the case for the larger group. Okay. So anyhow, I just consider this case in this talk. So one consequence of this fact that these test functions are in the Harish-Chandracharacters space is that in fact you can for any irreducible representation, you can consider the operator pair.F. Okay, and you can also consider its trace. In other words, the character of pi can be defined on these functions because they are contained in the Harish-Chandracharacters space. Okay, so this is also a consequence of that. I'm not going to discuss proof at the moment. I'm just going to run through the various steps to show you the structure of the theory, let's say. Okay, I'll come back to discussing proofs in the second half of the talk. Okay, so now, of course, our goal is to understand the space of test functions. Okay, we need to understand something about it. So this lemma tells us how big it is. Okay. Now, of course, since these test functions come from, just going back, come from this diagram, right? Basically, this map. So you certainly have to understand these maps, P's and Q's a little bit. Okay, so that's what I'm trying to formulate here. So this map P, right, which is given by formation of matrix coefficients, and those matrix coefficients lie in a Harish-Chandracharacters space. That's what the previous lemma says. Now, this map is actually MPW cross MPW equivariant, and it is invariant under the diagonal copy of OV. Okay, just to recall that this capital omega is the tensor product of the wave representation little omega with its complex conjugate, right? And each of those little omega is a module for MPW and cross OV. So since you have two of them, you have two copies of MPW acting and you have two copies of OV acting. Okay. So as a result of this equivariance property, we see that the space of test function is actually an MPW cross MPW submodule of the Harish-Chandracharacters space. Okay. Now, also because this map is invariant under OV diagonal, certainly it factors to the co-invariance of omega by OV diagonal. Okay, it factors to this. Okay, and now if you sum over the plus and minus, in fact, it's an isomorphism. It induces an isomorphism of the OV diagonal invariance, sum over epsilon with the space of. Okay, I guess then there should be no epsilon here. Okay. Okay, so yeah, that, and this part 2 is just the mirror image, okay, where you have the rows of MP and of W and V exchange. It's the same statement. Okay, it is about Q. Q is also equivariant for SO cross SO, and is invariant under MP diagonal. Okay, so I mentioned that, so this is a correspondence, so it's not a map, okay? But I mentioned that the third bullet point in that slide was that if you pass to the space of orbital integrals, then you actually have well-defined map, okay? Now, so that is the slide, this is the slide that explains this point, okay? Okay, so we have this map, this is the map P, I guess, P from omega to the test function of MPW. The previous lemma tells me what this first arrow, some equivariance property of this first arrow, right? We know it is OV diagonal invariant, okay? And it's MPW cross MPW equivariant. Now, suppose we compose this map with a further projection, okay? We project to the MPW diagonal invariance. Now, this third space here is the name I give it is just a space of orbital integrals. Why? Because any invariant distribution is just a distribution, it's just a linear functional on this co-invariance, okay, on this space of co-invariance. So okay, so this is the first arrow is P, and this is just a natural projection. So of course the composite is MPW diagonal invariant. Okay, so it factors through this co-invariant space. Okay, but by the previous lemma, the co-invariant space is just this space of test functions on SO. So I actually get a well-defined map from the test function on SOV to this co-invariant space, which I think of as the space of orbital integrals on MP. Okay? And this map is the map that, this map is the transfer map. Okay, when you descend the target to the space of orbital integrals. Now, moreover, this arrow is, of course, is still SO diagonal invariant because originally this P here, this first arrow up here, was invariant under SO diagonal. Okay, so whatever it is, I mean, this arrow is still SO. So it also factors further to this. So we get a map like that. Okay, and this is the map from space of orbital integrals on SO to space of orbital integrals on MP. And the lemma is that, in fact, this is an isomorphism after you sum over the epsilon, the plus and minus. Okay. So because of this lemma, if you have an invariant distribution, so let's say if you have a linear functional on this space on the right, which is a linear functional, a conjugacy invariant linear functional on the space of test function on MP, you can pull it back to get invariant linear functionals on SOV plus and SOV minus. Okay, and so now the following theorem makes sense because if you take, so suppose we have a irreducible tempered representation pi with data leaf pi tilde. Okay, then if you have test function f and f tilde in correspondence, then you have this character identity. Okay, so another way of saying this is that under this isomorphism here, when you take theta of pi tilde, it pulls back to theta of pi. Okay, so that is roughly half of my talk. So I run through those bullet points, except the last one. Okay, and now, so you might say that this theorem is giving you a relation between the characters of pi and its data leaf pi tilde. Yeah, okay. Then the question was like, what does it mean? I mean, how explicit is it? I mean, can you write up formulas? Okay, so if you think of these characters as functions on, say, regular semi-simple set, so how can you express one? What does this identity mean? I mean, in terms of expressing one function in terms of the other. Well, of course, you might say that it is only as explicit as one understands the transfer of test functions. Okay, because so what I want to do in the rest of this talk is mostly to give a geometric description of the transfer of test functions. Okay, and but before that, I like to give you a sketch of the proof of this theorem. Okay, because the sketch is quite short, it does take 2 slides, and so I thought that maybe it's good to just give you a sense of how one proves this. Okay, so I will do that first, a sketch of the proof of the character identity, and then so you can see that for almost half my slides will be on this last point, geometric description of the transfer. So I think before I do that, again, let me pause for any possible questions.
Hi, can I?
Yeah.
So you're saying any invariant distribution is a linear functional on that space you got, right?
Certainly, if you work just algebraically.
No, but I'm saying so that is not actually related with a physical orbital integral along a.
Yeah, no, that's right. I just call it that because.
Just gave it a name.
Yeah, I just give it a name, but it is not a ridiculous name because it is, it is the abstract avatar of the. I don't know, because maybe you think of orbital integrals as literally functions on the set of or the space of, say, regular semi-simple conjugacy classes. Yeah, so you can think of that, but so this is an abstract avatar of orbital integrals. Somehow it's the abstract thing through which any concrete object has to invariant object has to factor through. I mean, invariant distribution has to factor through.
Thank you.
Yeah, okay. Okay.
Vitek, can I ask you a question?
Yes, please.
is there some correspondence of conjugacy classes between SOV plus and MPW?
Yeah, there is. So of course there is a theory of endoscopy developed by Wenwei Li, right, for MPW, right, and this SO2N plus 1 is principal endoscopic group. So there is a correspondence of so-called stable semi-simple classes. Now, if I'm not wrong, maybe it is even possible to refine this to the level of not just stable conjugacy classes, but conjugacy classes. Okay, and I'll come to that later when I talk about this geometric description.
All right.
Yeah.
Good. Thanks.
Yeah. Okay, so let me give a sketch proof of this character identity. Okay, it's going to proceed through the Plancherel theorem, the Harish-Chandracharacters theorem. Okay, so suppose you take this phi, which is phi 1 tensor phi 2, okay, in this capital omega, right? So we have this projection map P and Q, right, to the space of test function. So P of phi, which is a function of MPW, I can evaluate the identity element, right? Because the map is just matrix coefficient. So when I evaluate identity element, the element G disappear. So it's just this inner product. Likewise for Q phi of 1. Okay, so P phi of 1 is the same as Q phi of 1. And it's just this inner product. Now, but we know by one of the lemmas earlier that P phi, which is in the space of test function, is actually a Harish-Chandra Schwarz function. Okay, so we can apply Harish-Chandra-Plancherel theorem to this guy. Okay, so we can get a spectral expansion of the Dirac delta distribution on the space on the Harish-Chandra Schwarz space, right? So P phi of 1 has a spectral expansion, and the term. So this is an integral over the unitary dual with respect to d Plancherel measure. Okay, and of course the support of this Plancherel measure is on the tempered spectrum. So I could just integrate over the tempered unitary dual if I wish. But the point is that for every tempered representation, the integrand is just the character. Okay. Likewise for Q phi of 1 is that. Okay. Now because the P phi of 1 is the same as Q phi of 1, of course these two integrals are equal. Okay. So, and you see that in the integrand, these are the two terms that we want to show are equal. Okay. Okay. So coming to the second slide. Okay. So this is the identity we got from the previous slide. Yeah, equal. But you see, it's not convenient that the domain of integration are over two different groups. Okay. So I want to replace this domain of integration, say over MPW hat, right, by that one, by the unity dual SOV. So how do I do that? Well, I have mentioned that there's this local Shimura correspondence, right, that give this bijection on the tempered unitary dual on the SO side and the tempered unitary dual on MP side. Now, so a result that I have shown with Ichino is in our paper called Formal Degrees and Theta Correspondence. So the results in that paper can be stated as that when you take the Plancherel measure on those two guys on the SO side, you push forward by theta. Okay, what you get is the Plancherel measure on MP side. Okay. Now, of course, all these Plancherel measures and so on depends on some Howe measures on the group. I have to choose a Howe measure on MP and SO compatibly for this statement to hold. Otherwise, there will be some scalars in front. Okay. I mean, I didn't want to go into this. This the normalization issues in this talk. Okay. Okay, and this is how we can replace this integral over MPW hat. Okay, because you have this Plancherel measure here. Suppose you just replace it by that. Okay, you will break this integral into sum of two parts, the plus part and the minus part. Okay, namely the one that is in bijection with SOV plus and the other part with SOV minus. And then finally, you're going to end up with just, you can move this integral from MP side to SO side. Okay, so the left-hand side of this first identity, by virtue of this, becomes an integral over SOV. But of course, the character here is character of theta pi. Okay? In other words, I have pulled back this integral from MP side to SO side by using this bijection theta, which also pulls back the Plancherel measure to the Plancherel measure. Okay. Now, so now this already looks pretty good. I mean, this is kind of like what we want to show, except that there are integrals, these two integral signs in front. If I could just suppress them, then it will be the character identity that I want to show. And I guess there is a fairly standard way to do that, which is to use a so-called Bernstein center argument. Okay, so that's all I'll say because it's supposed to be a sketch, so I won't explain this Bernstein center argument. Okay, basically you can, in other words, this identity holds not just like that, but you can insert test functions in front of both sides, and if you have sufficiently many of those, then you know, allow you to localize and get and remove the integral sign. Okay, so that is a brief sketch of the character identity. So I guess the main inputs is the Harish-Chandracharacters theorem, and also this result with Ichino. That okay, so that's so as I said, the rest of the talk will be on understanding transfer more explicitly. Okay, because otherwise it's not clear what this character, how much do you really know from this character identity. Okay, so it seems that, you know, the key to understanding this transfer is to so-called, that's just a one sentence, is to interpret everything in terms of the doubling seesaw. Okay, so the doubling seesaw is some gadget in the theory of Howe duality correspondence. Okay, I guess if you are familiar with the Howe duality theory, you know what this is. Okay, if not, I try to give a brief explanation, but I'm not sure I can do a very thorough job in this remaining time. Okay, so first let's see what is doubling. It's very easy. You take a space, you double it. Okay, so we have a symplectic space W. You can double it, W plus W. What does this minus mean? It means that on this second copy of W, you multiply the symplectic form by a negative sign. Okay, so instead of taking the same symplectic form as the originally given one of W, you multiply it by a minus. Okay, so we'll call this a doubled symplectic space. Okay, which I'll call math BB W. Okay, I know errors will denote it as W square with a square in a superscript. Okay, okay. Now one thing to notice is that this space contains two natural maximal isotropic subspaces, okay, Lagrangian subspaces, the diagonal copy of W, and this is where this minus sign, right, makes this diagonal copy of W isotropic, and also the so-called anti-diagonal, which I'll call W nabla. Okay. Likewise for V, you can double it and you have the diagonal, V diagonal and a V nabla as Lagrangian subspaces. So the point of putting this minus sign here is that this space is split, even though the V itself may not be split originally. After you double it with this minus sign, it becomes a split quadratic space. Okay, so also observe that actually, so you can take this V tensor the doubled W. Okay, it is actually the same as doubled V tensor W. Okay, because you know, from this first equality, I just put in the definition of both face W. I know both face is the doubled space. Okay, it's just W plus minus W, right? So I put it in, and then I mean, from here to here, I guess I can move this minus sign to the other side, so to speak. Okay, and then I get that. Okay, so that's doubling. Okay, so what is the doubling seesaw? Well, so now we have this symplectic space V tensor doubled W, which is the same as doubled V tensor W. Okay, in this symplectic group, we have two dual pairs fitting into a seesaw diagram. Okay, so in this diagram, you know, the diagonal lines means these groups are dual pairs. Okay, so for example, we have one dual pair here, we have another dual pair there. Okay, and the vertical arrow roughly means this is contained in there. Okay, it's not literally containment, but this maps naturally to there, and this diagonal embedding to there, to the product of the orthogonal groups. So actually, of course, you have the same seesaw diagram with the rows of V and W exchange. Okay, so in fact, you could enhance this diagram. You could go down on this first column. You can put the diagonal copy of MPW, and on this second column, you can go up. You can put O of the doubled V, and then you can. Okay, so but let's just look at this one. Okay, this is called the doubling seesaw. So seesaw because it looks like a seesaw, and it's doubling seesaw because it involves this doubled space. Okay, so now since we have two dual pairs here, so this direction, right, this dual pair was kind of what we have but doubled. Okay, so on this arrow we have omega and its conjugate. Okay, why conjugate? Because of this minus sign. Okay, you change the form, you conjugate the Weyl representation. But for this dual pair or this other dual pair, this is the new input, right? The dual pair OV diagonal and MP of the doubled space. It has a Weyl representation too, which I will call capital omega. Okay. Now, of course, the left-hand side is a representation of these two groups. The right-hand side is a representation of these other groups. And but the common part is the bottom row, right? So you can restrict both sides to the bottom row, and they are isomorphic. Okay. These are just some facts. Okay, so now I reproduce this. Okay, we have an isomorphism when restricted to the bottom row. And okay, so the point to notice here is that this right-hand side, right, this omega tensor omega bar is precisely the domain of our maps P and Q in the definition of the space of test functions. Okay. And when we were earlier, okay, we had, to simplify notation, we have denoted this tensor product by capital omega. This is consistent with this notation here. Okay. But so what do we gain by this? What we gain by this is that this domain, omega, capital omega, actually has this, it is a Weyl representation for this other dual pair, MP double W and OV diagonal. Okay, so we are going to use this feature to help us understand these maps P and Qs. Okay, so we want to interpret the map P and Qs through the lens of this other dual pair. Okay, so so what does that mean? Okay, so for example, we have mentioned before that this map P is OV diagonal invariant. That was one of the lemmas, right? So it factors through the OV co-invariance. Okay, now the point is that because this omega is a representation of OV diagonal with a commuting group MP double W, this co-invariant space is not just a vector space. It actually carries an action of MP double W. Of course, we know that it carries an action of MPW cross MPW. Okay, and in fact, this map is MPW cross MPW equivariant, but in fact, it has action by a larger group. Okay, and the point is that one understands this module of MP double W. This is a result of Raleigh's. Okay, so I will describe this result of Raleigh's on the next slide. So Raleigh's result basically says that when you sum this co-invariant space, okay, recall that we have the V plus and V minus, and it's always better. The result looks nicer when you sum over those two, okay, the pure inner form, so to speak. When you sum over them, of course, so this is a direct sum of two MP double W modules. And it turns out that it is nothing but a certain degenerate principal series. And the zero refers to the fact that I'm at the, I'm using the trivial character, okay, in this case. All right, yeah, okay. So the right-hand side is a degenerate principal series. Well, induced on what parabolic? So on the Ziegler parabolic, stabilizing the maximal isotropic subspace, W diagonal. Okay, so that's what Raleigh says. And in fact, he tells you what this isomorphism is, okay? Maybe I call iota the composite of the isomorphism with the natural projection map. Okay, so this map iota can be very easily described. Okay, so first, the space itself, this capital omega of epsilon, is very concrete. It is just a space of Schwartz function on the vector space. Which vector space? V epsilon tensor W nabla. Okay, whatever it is, this is just V tensor W. Okay, so let's take this model of capital omega. It's just Schwartz function on this tensor product. So given a Schwartz function, iota will carry it to an element in this induced representation. This induced representation, so I will tell you which element it is, but elements in these induced representations are functions on MP double W, right? That transform in some way, with sort of character under this parabolic P. Okay, so to tell you what this function is, I evaluate at G, and it's just given like this. Okay, you just let G act on phi and evaluate at 0. The action is, of course, given by the, this WIS representation action on capital omega. So that's just something we gain by looking at the doubling seesaw. Okay, I just want to write down to show this is a very simple map, very explicit and very simple map. Okay, so now it's good because we want to, going back a bit, we want to understand this space. Okay, but this space is mapped from that space, and now we understand this space. Okay, it's just a degenerate principal series. Okay, so I want to, and moreover, it's just an isomorphism, right? We say that. Okay, so very good. So that's okay. So then now we need to understand this degenerate principal series from other points of view. Okay. So as I mentioned, elements of the degenerate principal series are smooth functions on the group that transform by some characters under P. So you can think of these as smooth sections of a line bundle on this partial flag variety. Now, since they are smooth sections, they are determined by restrictions to any open dense subsets. Okay, because it is like continuous function is determined by their restriction to an open dense set. Okay. So we are going to choose, so there'll be two open dense sets that are relevant to us. Of course, the most natural one, or the first one that comes to mind, might be something like the open Broussard cell. Okay, so in other words, you take this certain longest vowel element, W0, and you look at P, W0, N. N is the unipotent radical of P. Okay. Now, note that in this case, N, we're in a symplectic group, so this N is like symmetric matrices, right, on the upper right hand corner. So it is isomorphic to the symmetric square of W diagonal, okay, which I remind you is basically the Lie algebra of W. Okay? So that is one example of open dense set you could use in such a restriction. But the other one is that when you look at SPW cross SPW action on this SP of the doublet, okay, on this flat variety, there's an open dense orbit, namely the orbit of W diagonal. Okay. The stabilizer of the orbit is just a diagonally embedded copy. So in fact, this space X2, right, is, it's just, you can identify with, for example, the first copy of SPW here. Right? Because, this cross this mod diagonal is just the first copy. Okay. Okay, so we have these two subspace. We're going to, okay, so in other words, we have two injective restriction maps, right? You give me some section in this principal series, I can restrict it to, so here, for example, I restrict it to the open Broussard cell. Then I'm just going to get some smooth functions on N. Okay, maybe I should write W0N, but I just identify it with N, okay, which are smooth functions on the Lie algebra. Okay. On the other hand, I can restrict to the other open set, which is, as I said, is just a copy of SPW. So over here, I just work algebraically, but here I just remember I'm on the metapractic group. I can restrict to that, and I get smooth functions. Okay, and in fact, this first restriction is just the map P. Okay, P is just iota composed with this restriction. Okay, and in particular, we see that this restriction map gives an isomorphism of the degenerate principal series with the space of test functions as MPW cross MPW modules. This actually is not, this is quite easy to show. It's just from the formula, because what is iota? Iota was explicitly given and so on. So, okay, so now let's denote the image of the other restriction to the open Broussard cell. Just call it S of SPW. Okay, think of it as some space of test function on the Lie algebra. So of course, we also have isomorphism of this degenerate principal series with this space. Okay, so now in particular, we can think of our test functions on MPW as a space of functions on the Lie algebra. Okay, now we can ask what this isomorphism from the first term to the third term is, and the answer is it is basically a Cayley transform. Okay, it's basically a Cayley transform, although it's slightly twisted or normalized by this factor here. Okay, so C is, so there is a is what I call birational map from the Lie algebra to, it's not so accurate to call it birational, right? Because MPW is not algebraic, okay? But I guess what I mean was there is a map defined on an open dense set from SPW to MPW, such that when you compose with a projection to SPW, it is given by this formula, which is the Cayley transform. Okay, and of course it's not defined everywhere. Right? It's defined on some open dense set. Okay, and actually this map is just the identity map as far because you are taking the intersection of x1 with x2 is an open set and then an open dense set, and you are just saying that if I have an element here, you know, what is the relationship or the coordinates when I write it in, you know, the coordinates in the open Broussard cell or the coordinates in this SPW. Okay, so it's basically just Cayley transform, but you know, twisted by okay. So the function, so the isomorphism sends a test function f on MPW to a function on the Lie algebra and phi. Okay, and they are related in this way. You pull back f by the Cayley transform, but you have to you know, there's weighted by this factor. Okay, so now because of this, right? So instead of working with this space of test function of MPW, I can work with this version or this avatar of it. It's functions on the algebras. Okay, so as a summary, so at the moment we have this diagram because this first top of the diagram was what we had originally when we defined the spaces of test functions and the transfer. But now what I said was that, you know, there are the Cayley transform define isomorphism from this space of test functions to that one, and likewise on the other side. Okay, now, so let's ignore this. So now let's replace the functions on the groups by functions on the Lie algebras. Okay, so we have omega mapping to functions on Lie algebras. And it turns out that this sort of diagram arises in another way, so to speak, namely in the moment map associated to this symplectic variety. Okay, because V tensor W is symplectic vector space equipped with this natural action. This is a Hamiltonian symplectic variety. So there's an associated moment map. Okay, so this moment map is, you know, I guess it's a map from the symplectic variety, V tensor W, to the product of these two Lie algebras. Okay, but I write it as a double fibration. It's given in this way. The maps are very concrete. And what I want to say was that this this diagram is very much, it behaves, you know, the properties of these P prime and Q prime are very similar to the P's and Q's earlier. Okay, and the point is that, so I think I'm running out of time, so let me run through this quickly, almost at the end, is that when you look at certain open subsets corresponding to, I mean, basically the set of closed orbits, right? Which correspond to maximally non-degenerate maps, okay? Because, you know, elements of V tensor W can be thought of as maps from V to W or W to V. Why? Because V is equipped with an isomorphism to V star, to its dual space, because it has a symplectic, I mean, it has a non-degenerate form on it. Okay. So my point, so what I said here was that if you pass to a certain open set, then which is the set of closed orbits of, it's kind of the regular semi-simple orbits, okay? Then there's a bijection of the orbits, not just the stable orbits, but literally orbits. And it's induced by this moment map picture, okay? So we have this picture of the moment map, and if we take, you know, say compactly supported functions, we can integrate along fibers. Okay, and so this diagram looks very much like the diagram we had earlier for the P with the P's and Q's. Okay, and the point is that just like before, you can show that this, when you pass to the space of orbital integrals, in other words, this co-invariance. So using this diagram, you can define a correspondence, right, between test functions on these two spaces of test functions. Okay, just like before, and it's just a correspondence. But when you pass to spaces of orbital integrals, this co-invariant space, they become isomorphic. Okay, so now it is, I think, natural to ask whether this moment map correspondence is the same as the one that we have, and the answer is no, not quite, but they are related by Fourier transform. Okay, so that's what this proposition is saying. Okay, they're related by Fourier transform. Now here, the Fourier transform is in a sense of distribution, because when I do the integration by fibers, I just get functions on an open set. Okay, so I have to interpret this as distributions. Okay, so in other words, to summarize, the geometric description or transfer is you give me two functions f tilde and f. I first think of them as use the KD transform to move them to think of them as functions on Lie algebras, and then I say that they correspond if their Fourier transform have the same orbital integrals under the moment map correspondence. Okay, so another way of saying this is to say that if you take the one of these orbits, right? It is an invariant distribution. Okay, so you can take its Fourier transform. It's still an invariant distribution, and that Fourier transform of O, okay, will be transferred to Fourier transform of O tilde. Okay, so that's another way of saying this thing. Okay, so I think that I will stop here. So I have a couple more slides. Maybe I let you take a look on your own. So okay, I think I stop here. Sorry for going slightly over.
Thank you very much. Any questions, please?
Hi.
Hi.
I'm just asking, is there any Kirillov-like character formula for periodic groups?
So is there any character formulas for?
Like Kirillov's, that Fourier transform of a coadjoint orbit is locally the character.
Yes, there has been. So I guess in the real case, I guess you are thinking of theorem, the results of Rossmann, right?
Yeah, exactly.
That is, yes. So I think in the periodic case, as far as I know, there are some results, but I don't know if the result is as complete as in the Archimedean case. So I think there are results of Fiona Monahan that try to express the characters of some supercapacitor, which are obtained as compact induction from an open complex subgroup as Fourier transform of some semi-simple orbits or something like that. Okay. Now, of course, there are ongoing works of Lawrence Spice and Jeff Adler, Stephen DeBarker that proves character formulas, very explicit character formulas for compactly induced supercapacitor. But I think those formulas, they're very explicit but they're not in the same spirit as what you're thinking of, meaning writing it as Fourier transform. Yeah, so I think that's all I know about this. Yeah, but I think it's a good question, like whether, yeah.
Okay, thank you.
Yeah, you're welcome.
I have a question. Can you derive from your equality the relation between wavefronts of two representations as being defined by a character, not via Moglen-Walsh-Porcher model?
Okay, so okay, the answer is I have not thought about. I mean, I'm aware that this is one thing what you want to do, because I think that is one of the applications that Prashbinda did with his in his paper. In fact, you might say that was the reason why he proved this character identity. He was trying to prove some conjectures of how about relation of wavefront sets of pi and its data leaf. So certainly this is, but I have not gone so far yet. I have not gone beyond what I told you in some sense. So yeah, so I think it's possible. It should be possible, and especially when you realize how the how this transfer of function can be described geometrically in terms of the moment map. So I think from there, if you work on, I think you should be able to deduce this relation. So you do the local character expansion on both sides and compare the leading terms or something like that.
Mm-hmm. Okay.
But I personally haven't done it. So.
But you have it already. I mean, you have it in Cayley transform, and you have the Fourier transform.
That's right. Yeah, I guess these are the ingredients that will allow you to arrive at that result. But since I haven't done it myself, yeah, I hesitate to claim that. But I think it's something that I think for you, I think for Thomas, I think that you probably can do it with both eyes closed. But I cannot say that for myself.
There is also work by Chen Bourgeois and Raul Gomez, or do they work with the full theta and not the reducible one?
Yes, but I think their approach is they work with the Gelfand-Greif models. They are computing Gelfand-Greif models. The relation of Gelfand-Greif, I mean, these are different periods, right? The Fourier coefficients.
That's true.
Yeah, and then then you can appeal to Mogren-Wasper-J, for example, and to relate to the local character expansion.
But in the non-Schmidt case, right? And but there is also a locand map for associated varieties in the real case.
Yes, that's right. That's right. So I think that yeah. So I think that what Tomasz was trying to do was to use the character identity to derive these relations, whereas other people are using k types or some periods, Fourier coefficients, and so on.
And guess, is there also a difference that they work with the full theta and you work with the reducible one, with the reducible quotient? Or?
No, because in this case, if I was working with tempered, right? In the tempered case, the big data and small data are the same.
I see.
No, I would say that I think that in general, this type of argument will get you handle on big data. I mean, it's a challenge to pass to small data.
In general, it's a challenge to pass to small theta.
Yeah, that's right. That's right.
I see.
So can you just clarify again, what's the best way to view this space of test functions? You just relate them to sections in the degenerate principal series? It's just it, or the test potential? How again? You mentioned it, but
no. I mean, it depends on what you. What is best depends on what you want to do. If you just want to give the quickest definition, without any introducing too much notation, so you just say it's the space of matrix coefficients, right, of the WIS representation.
Yes, but you have described it in yet another, at least two ways, right?
Yes, I mean, I guess it is. As I said, it's just it's through this doubling seesaw, and that's right. I mean, as I said, it depends on what you want to do. So if you just want to state results as neatly as possible, I think I would just say that it's just a space of matrix coefficients of WIS representations. Now you want to prove that it is related. You have other. But when you want to describe this, to understand this space, you try to view it from other viewpoints, and certain viewpoints are better for certain things you want to do.
So if you just want to describe them as functions on Lie algebras, what kind of functions are those?
Yeah, so that's a good question. Okay, meaning like so because you might want to say that can I write down its functions on some open dense set of the Lie algebra? You can even explicate what this open dense set is. Okay, and then you can say that it's smooth functions on there, and maybe you want to describe this space of functions by its asymptotics towards the boundary. I didn't think about this question. I think that, but I think this question is just a question of the following type. You have a degenerate principal series induced from P to G of some character, right?
Mm-hmm.
And you know that you have the open Broussard cell. Let's say you take the opposite unipotent n bar, right? So you restrict your functions to n bar. This is an injective map. You don't lose information, and then you ask what functions do you get, right? It is this quite general. This is the general question, and I don't know if what is the. I don't know of a general answer. I don't know if people have tried very hard to think about general answer. Certainly, you know that whatever space it is, it contains the compactly supported functions.
Yeah, but the asymptotic has to do with Jacquet modules of the.
Yeah, I guess yes, that's right. That's right. So I think it may be doable. I didn't think about that, but I think that you'll be good if you want to really explicate it and describe it. I think. Instead of saying that it is obtained in some way, right, as the image of some map, you may want to give a more intrinsic characterization in terms of its growth or asymptotic properties.
Mm-hmm.
I think this is a good thing to think about. Yeah, but I think that the main point for me, you see, for me, for a long time, I wanted to describe this transfer geometrically. I didn't know how to do that. Okay, then I thought maybe I should pass to Lie algebra level, linearize it a bit, right? And then I thought, okay, use exponential map. Okay, but then it didn't really work out too well or too easily. Okay, but then and then I thought, okay, maybe let's use Cayley transform, okay, because we know what Cayley transform is, formula, okay, but even after you transfer, you're working with these formulas, but it's not clear what you should do, okay. So then I think that the point was to view it from the point of the doubling, whereby you have this large ambient space, which is this degenerate principal series, and all these other manifestations of your of your different spaces of test function are simply different manifestation of this degenerate principal series, right? You are just taking the functions there, restricting to different open sets.
Mm-hmm.
So if you want to know the relation, you can always pass back to this universal guy, so to speak.
Mm-hmm.
So that's so for me, it explains it better, because otherwise, if you don't use this guy, then you might be forced to work out the formula somehow. And for example, right, the relation, just now I say it was Cayley transform, but not really, it's Cayley transform, but sort of weighted or normalized by an extra factor, right? And there's no way I can guess that somehow. I mean, I have no intuition to guess that, but it is what this degenerate principal series gives me.
Okay, thanks.
I was wondering, so in the real case, we have this transfer from orbital integrals without any stable range assumption, but it is based on a characterization of orbital integrals due to Boisys. So if you have, let's say, only algebra. So if you have Kaplan subalgebras, you can consider the orbital integrals. There are some distributions on the regular set. They have to match by some jumping conditions. Mm-hmm. And so this is characterization of this orbital integrals, and it was quite a pain in the chair to check that everything works for this Harish-Chandra integral, that I really do transfer. Someone I can't. I would have to read your stuff. Where does this difficulty disappear?
I have no idea. I have no idea, to be honest.
Yeah, so you nuke it with Harish-Chandra's Plancherel formula, right? I mean, you use this nuclear bomb. Maybe that's what it is. I don't know how this difficulty disappears.
Yeah, so obviously I looked through, I poured through quite a number of your papers to see if I would recognize now some of the formulas, and some of the formulas I could actually recognize now. And but I have to confess, I do not fully understand this Harish-Chandra, Cauchy Harish-Chandra integral yet. And yeah, so in fact, I don't know, how.
Okay.
Yeah, I don't know. Yeah, so you're right. So of course, because there's hardly any analytic things I said, right? So.
So what are the orbital integrals for you?
So as I said, for me, it's just this abstract co-invariant space, right? You have functions on G, and you look at the co-invariance under the conjugation action of G, right? So this is our abstract space, but it is somehow anything like any maps which is conjugacy invariant will factor through this.
Yes. So this is even.
So this is the abstract space on which all invariant distribution lives, so to speak.
I see.
And I just compare at that level. So I don't actually work with integral the function over conjugacy classes.
So maybe simply you get it less explicit, right? I mean,
that's true. Yeah. So you may say that it's like the point is exactly like how you think of the characters. You can think of it as a function, right? Or you think of it as a functional on this co-invariant space.
Mm-hmm.
Yeah, so I agree with you that maybe you say that, now let's write down the function, like on the conjugacy invariant function on regular semi-simple set. And then when you try to explicate these things, you will definitely, but I think that enough information is provided to actually write down some formulas. But of course, maybe these formulas may not literally converge, because, some of them is like Fourier transform distributions and so on. So you have to maybe make sense of it in some appropriate way. And maybe that is where the difficulty in your papers are.
So, I mean, the outcome is that if you give me precisely what this character of one group on every Cartan subgroup, then after a gallon of coffee, I'll tell you what is the character corresponding to it. What is the outcome on the other side?
Yeah, so I think that this is like, yeah, so here I just think of the character as this invariant distribution on this co-invariant.
Yeah.
I mean, just a distribution on a linear map on this co-invariant space, and somehow, yeah. So,
yeah, but
so for me, I think for me it was yeah. So I think that one can still go even more refined or explicit than what I've said today. Which is to, as you say, to just think of it as a function on the regular semi-simple set, and write down this character identity explicitly as an integral transform. Yeah. So for me, I would say that because my main reason for doing it was actually to have
this integral transform. Yeah, this integral transform. Yes.
I wanted to understand the easy part, let's put it this way. So the part which is supposed to be easy and formal and so on, I want to isolate it out and just understand the mechanism. Yeah, so
it's very nice. So this integral transform, in the real case, it becomes either a Cauchy integral or Dirac delta or Poisson integral. There's three things, and then you can compute stuff. But yeah, this is so in the p-adic case. I have no idea, but there is no such thing like characterization of orbital integrals in terms of
there is
subalgebras.
No, there is a characterization of the space of orbital integrals.
Oh, okay. So
certainly.
I mean, just like these jump relations for the reals.
Yeah, it's basically it's smooth on the regular set, but then as you approach the singular set, there's some asymptotics given by these so-called Schleicher germs. So there are conditions like this, in terms of asymptotics towards singular sets.
And in your argument, this doesn't play any role, right?
No, because I don't physically realize all these things as functions on the regular semi-simple set. I think of them as I said, linear functional on this co-invariant space.
Very nice.
Yeah, so I think that we can try to explicate it further, and probably at that time we will run into the difficulties that you were dealing with.
Can you do the same things in the non-equal rank case?
Yes, you can do it in a non-equal rank case.
Do you know the
so
formula?
Here's do I know the formula? It should be the same setup. Okay, but I tell you what the difference is, right? So in this case, where both space of test functions are contained in the Harish-Chandracharacters space, but in the non-equal rank case, only the test functions on the smaller group is L2, okay? But the other one is not. In fact, if you just use this PQ diagram, right, you get a space of functions on the larger group, which is very small. It's a very small space of functions, okay? But this small space of function is enough to detect the small family of representations, which are data leaf from this very small group. Because your group is very big, there are many representations, right? The dimension of the space of representation is like the rank of the group or something like that. So, but you are only interested in those which are data leaf from this very small group. So it's a very thin family, right? And to detect a thin family, you just need this thin space of functions. They are not L2 even, okay? And so you will get identity like that, which you may not be so happy with because it's like, the Harish-Chandracharacters character is supposed to be linear functional and compactly support all compactly supported function and not this, God knows what space of function it is. Okay, so then, but there's a way of replacing this space of function by a larger one, which contains the compactly supported function and is in the Harish-Chandracharacters space. This space of function is somehow a quotient of that one, meaning there's a map from one to the other, okay? And from the point of view of this doubling seesaw, what you see is that on this large group where you get this small space of functions, you are getting the degenerate principal series at the negative point. So for example, -2, right? And you don't like that, okay? So, but you have this functional equation, I mean, the intertwining operator, right? That could go from the positive point, say I of 2 to I of -2. So you can work with that space of function at I of 2. It will be like our space at I0, which is, is squeezed between the compactly supported function and Harish-Chandracharacters space. Then the intertwining operator, okay, will give you a map to this smaller space. And so you can pull back everything to this larger space, and you can then somehow, so there are these complications that come in.
But then what is the statement about Fourier orbital integrals of Fourier transforms? You have a similar statement?
It will be, yes, I guess so. You will have such a thing, but you'll be more singular, I guess. So meaning just now we just have functions as our open set, right? So here we may not. I mean, it may be like, it has to be understood in the sense of distribution, because it may be like, you know, they're like function, when you do this integration on fibers, right? You may just get, because one space is very big, one space is very small. So on the small space, you get essentially everything, let's put it this way, okay? On the large space, there's a very thin family, which may be like function supported on some smaller set, right? So, and you have to do Fourier transform of that in the sense of distribution. Yeah. Then, so the setup is largely similar, but for this fact that you have a very small space of functions. Now, if you're happy to live with it, you can just leave it as it is, but actually it's not so nice. It's better to work with this, you know, at least you should contain all the completely supported functions, so to speak.
That would be very interesting, though, to say, because it encodes the transfer between a small group and a much larger group. So, okay.
Yeah,
it would be very
exactly. I agree. Yeah, I agree. So and it also puzzles me why, right? At least from my point of view, the equivalent case was somehow easier or cleaner to describe. But from Brechbinder's point of view, like the stable range was somehow easier, because that's the case that he did in detail. And somehow, once you pass out a stable range, it becomes harder for him. Yeah, so I don't fully understand why. So
I did it just for the reals.
yes, but yeah, but surely you can do it for p-adics.
If you see Locke, wake him up, okay? Because I'm working on it with him.
I see.
Yeah, can I ask yet another question? Can you go to your slide 27?
27.
Please. Yes, so this diagram in the bottom, what's the equivariance properties of it? So
the equivariance. So P is MPW cross MPW equivariant, because you have the left and right translation action on the target.
But you also have an action of OV, right? Like you have V only on the upper left bottom.
Yeah, so you have an OV. So at the top, you have OV. Okay, so yeah. So actually, in this diagram, I just care about OV as an MPW acting geometrically.
Yes.
On the top. Okay. And this MPW action is the diagonal MPW action. So this map is MPW equivariant, where the MPW action on the target is by conjugation. The horizontal map, the Cayley map is equivariant with respect to conjugation. The MPW action by conjugation.
Mm-hmm.
I guess so is Fourier transform and this map. Yeah.
So
on these three corners where you have
of geometric action of
that's right, just geometric. On the left, upper left corner is geometric action for both OV and MPW, and on the other three, the MPW action is by the adjoint action, and I guess the OV doesn't act, so OV acts trivially.
And SPW hard is just an open dense subset of SPW?
Yes. It is kind of like analogous to like regular semi-simple conjugacy classes.
So the image is Fourier transform will be not onto, will it?
No, yeah, exactly. So by integration along fibers, I get smooth functions on this open dense set SPW hard. Now, this function, so I don't define them on the whole of this, right? So, but I can treat them as distribution. I can integrate against compactly supported function on SPW. This integral actually converge because you can pull it back to the top of this moment map. I mean, maybe to here, and it converge. Okay, so now I take Fourier transform, and part of the assertion here is that take Fourier transform of this distribution, you land up in this space that you get from the Cayley transform, let's say.
Okay, thanks.
I wanted to ask a question about probably two slides which you didn't show up because
Sure.
About the global thing, because we personally encountered this kind of a situation when you have a big representation and the small embedded groups, and then you end up with a formula which is usually called Voronoi summation formula, something like that. And probably you're getting something here, also some summation formula which relates L functions or periods on two different groups.
Maybe this slide you mean?
Yeah.
So okay. So this slide I said that, you know, is that this, whatever I'm doing for this talk, it actually works more generally in the setting of relative Langlands program. And the point was that when you have a dual pair, right, it's typical to have a relation of a certain period on G with another period P prime on H. Okay? And with any of such period, which means some invariant linear functional, right, you can have a relative character, and you can then ask whether relative character are respected by Theta correspondence. Okay? And the case I discussed is for the case where, you know, G is like MPW cross MPW, and H is OV cross OV, and the period is the diagonal, you know, period, right? So and in that case, the relative character is just the usual character. But you can do other
relation
cases.
Between two periods on different groups.
Yes.
Period to period. Okay.
Yes. So I think I gave two examples here. One was a paper that was on the archive for a year already with my student Xiaolei Wan. So here, for example, if you look at dual pair SL2 and ON, let's say N is even, right? Then you can look at Whittaker periods on SL2 and ON minus 1 period, and they are related by Theta correspondence. And there will, you know, there's some character identity, relative character identity. And Xiaolei's thesis deal with another example, SO5 mod U2, okay, where now this period is related to a Whittaker period cross a torus period. Okay, the torus is determined by a quadratic extension that defines this unitary group U2. So what is the dual pair here? Well, SO5 is PGSP4, and PGL2 cross PGL2 is PGSO4. So it's basically the data correspondence for these similitude pairs, similitude groups.
But do you have formulas produced that way which will relate sum of periods of some representation to sum of periods on the other thing?
So I see. So I think that, you know, of course, you know, if another approach to proving this type of thing is through the relative trace formula. And if you do a relative trace formula, I think what you get is something like what you say, is because the relative formula just treat the whole spectrum, right? You're going to get a spectral expansion, sum over representations of certain periods is equal to another sum over other representations on another group of some corresponding periods. And by choosing your test functions, you can pick out the family over which you are summing appropriately, perhaps. And maybe that's what you mean. So I think that from this data point of view, right? So I think in the relative trace formula point of view, one usually get an identity like that, right? A sum of spectral expansion equals another spectral expansion, and then one try to isolate terms to get. It's just kind of like, you know, your two integrals, you have to remove the integral, right? But from this approach, by data correspondence, you don't go through this sum or average. You immediately get the term by term spectral transfer, and yeah. So I guess you could, after the fact, you could you could do a sum if you wish.
No, I
Yeah,
understand,
so
but, I was asking, maybe there are certain situations where you don't get this term by term relation. Okay.
Yeah, no, I would say the data correspondence is essentially one-to-one.
Yes,
although in this last example, right, SO5 mod U2, actually the period is not, I mean, the multiplicity is not 1, it could be 2. So there's higher multiplicity, which means that when you write down the global period, it's not going to be factorized. I mean, a single period is going to be a sum of 2 global periods, something like that. But so where is this multiplicity accounted for, since we are using data correspondence? Well, it comes in the following way, that in data correspondence, you should really work with orthogonal group, not special orthogonal group, right? So when you, but here, because when you work with special orthogonal group, it becomes like 2-to-1, so to speak. And that's where the multiplicity comes from. But maybe this is not what you have in mind in your question.
No, I just wanted to see what examples you can produce that way.
Yeah, no, I think these examples are largely one-to-one, and well, it is what it is.
Okay, great. Thank you.
Do you have a moment map for arbitrary dual pair?
I mean, if it is just in the sense of the talk, yes, the moment map is for any V and any W, any size, doesn't matter. But if you're asking the context of these periods, actually, that's a good question.
G and H.
You mean just this in this last slide here?
Yeah.
Where you are, okay, so one should be able to write down a moment map correspondence for these periods. There are, but I don't know how. And I know that in Yanni's papers where he defined in other ways, right, this transfer, right? He did make use of moment map. At least I see this word appearing in his papers. But I would say I did not fully understand the mechanics of it, so to speak. But I believe that in this data case, where when you have this one period related to another by data correspondence, there should be some analog of this moment map picture for the periods. And I think maybe Yannis would probably know this already, like what it should be.
No, I didn't understand the mechanics of it either.
Yeah, but you use it in your paper, right? You have maybe you try to even use it to motivate something.
Yeah, I use it, but I don't know. I use it to compare the Whittaker period to other periods, but I don't know the meaning of it and how it what happens in higher rank.
Yeah, so I think that's a good problem, good question to understand. I mean, that because I feel like for example, these 3 examples, it should be everything is parallel, right? So since we have this moment map, there should be one here, and yeah, I should say that in this example of ON mod ON minus 1, we also have a transfer and we have a geometric description of it, but we're writing a formula as an integral transform, and well, okay, so. But it's somehow not very. But I don't know of a systematic way. Let's put it this way.
Okay. Thank you very much, Vitek.
Oh, you're welcome, Dima.
Next week, we have Solomon Friedberg speaking about some generalization of theta correspondence, if I understand correctly. So see you next week at the same Zoom link.
Thanks.
Okay, see you, everyone.
See you.
Yeah.
Thanks for staying late.
Oh, yeah, no problem. Going to bed now.
Good night.